Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.5. Continuity.
Lesson 3. Continuity on intervals and algebraic functions. Part 2. Okay, so now let's look at algebraic functions that contain roots. So we're going to be looking at functions that contain square roots, cube roots, fourth roots, and so on. And what we'd like to do is figure out the continuity of those functions. So let's look at this example, f of x equals square root of x. In fact, you probably remember what that function looks like if we were to graph it. I'll just squeeze the graph in here. It's the top half of a parabola that opens to the right and has vertex at the origin. So it looks something like this. F of x is equal to just the positive square root of x, and so we just get the top half of a parabola that opens to the right. So that's the graph of f of x equal root x, or you could think of it as y equals square root of x. And the first thing we're asked to do is to find the domain of this function. Well, remember that for a square root function, we can't take the square root of a negative number or else we get an imaginary number. So we can only take the square root of a number that is positive or 0 at the smallest. So the domain you could write is all real x greater than or equal to 0, or another way to say it is it's the interval from 0 to infinity where we include 0, because square root of 0 is defined, that's just equal to 0. So the input has to be positive or 0, and you can also see that from the graph. The graph only consists of x values that are 0 and greater, so only 0 and positive x values can be put into this function. Okay, well, now what we want to do is try to show that f is continuous at each number a in its domain. That would mean it would be similar to polynomials and rational functions, which you may remember we just showed are also continuous at each number in their domain. So let's go ahead and think about this. In this case, we have a function that's got a domain that is the following. It's 0 to infinity, including 0. We put a square bracket here. What I'm going to do is to go ahead and think about two different cases. First of all, let's think about a case where we're thinking of a number a that is in the open interval from 0 to infinity. In other words, a is some positive number, some positive real number. And so that'll be case 1. And then separately, we're going to think about the continuity at 0. The only thing we could hope for here really is continuity from the right at 0. Since we have no portion of the graph to the left of 0, our function isn't even defined for x's that are less than or to the left of 0. So first, let's just think of this as sort of case 1, where we'll just think of a positive real number. A is in the interval from 0 to infinity. In other words, a is greater than 0. Well, let's check the definition, the careful definition of continuity for such an a value. Remember, we have 3 conditions to check, and the first condition is that we want to be sure that f of a is defined. Well, is f of a defined? F of a for this particular function is just the square root of a, and as long as a is a positive number, we can take the square root and get a real number output for that. So yes, f of a is defined and it equals square root of a. Second condition in our careful definition of continuity is that the limit as x approaches a of f of x has to exist. So that's our question. Does the limit as x approaches a of f of x exist? Well, let's go ahead and figure out what that limit is. The limit as x approaches a of f of x for this function is just the limit as x approaches a of square root of x. And remember that we had a root limit theorem that said that the limit of a root of a function is the same as the root of the limit. So what I'm going to use here is the root limit theorem, and I'll abbreviate theorem this way. And that says that I can pull the square root outside, or another way of saying it is that I can pull the limit sign underneath the root, the square root in this case. And, excuse me, so I would end up with limit as x approaches a of square root of x is the same thing as the square root of the limit of x as x approaches a of just x. So I've pulled this limit sign inside the square root. That's usually the way that we say it. Okay, now the question becomes, can I compute this limit that's inside? Sure, it's just the obvious limit, or you can alternatively think of x as a very simple polynomial, so we get to do it by direct substitution. And what do I end up getting? I get square root of, and it's the obvious limit, so I just replace x with the number that x is approaching, namely a. So I get square root of a as an answer. Well, what does that mean? In part 1, we said that f of a is defined, and notice it ended up being square root of a. In part 2, that condition was also satisfied. The limit as x approaches a of f of x did exist and ended up equaling the square root of a. And of course, the third part of our definition of f being continuous at a is that the limit as x approaches a of f of x has to equal, so put a little question mark here, f evaluated at a. So the values the outputs are getting close to as x gets close to a has to be the same as the value is when I plug a into the function. Well, is that true? Sure. In part 1, we found that f of a was just equal to square root of a, and in condition 2, we found that this limit existed and was equal to square root of a, and those two things are equal to each other. So the third condition of continuity is also satisfied, and that means, I'll put therefore, f of x equals square root of x is continuous at any x equal a where a is something in this interval. A is contained in the open interval from 0 to infinity. So we've shown that f is continuous on most of its domain. It's continuous for all the x values that are greater than 0, but we haven't yet shown that it is continuous at 0. Well, of course, the function isn't actually continuous at 0 because it's not even defined to the left of 0. So it won't be continuous at 0. We can't talk about the limit as x approaches 0 from the left because the square root of x is not even defined for values of x that are less than 0, that are negative values. However, remember that we could say it's continuous on this, I guess, half open interval that's closed here at 0 if we could show that it was continuous from the right at 0. So we'll try to check that the limit as we approach 0 from the right is exactly the same as the value of the function at 0. Let's do that on the next page because we've just run out of room here. So we've done case 1. That was this case right here where we showed that our function was continuous on this part of the domain from 0 to infinity. And now we're going to do case 2 where we try to show that our function is continuous from the right at 0. And that would mean that our function root x is continuous on the entire domain. So case 2, I'm going to go ahead and say, let's show f of x equal root x is continuous at least from the right at x equals 0. If we could do that, then we could say it's not only continuous on the open interval from 0 to infinity, but we could say it's continuous on the interval that contains 0, that's a half closed interval or half open interval. Okay, let's go ahead and see if we can do that. Well, how do I show that something is continuous from the right? It's essentially the same 3 conditions. First of all, I have to check that f of 0 is defined. So let's ask ourselves, is f of 0 defined? Well, what is f of 0? F of 0 for this function is square root of 0. And yeah, square root of 0 is 0. 0 is a number I have to square in order to get 0. So yes, it is defined. So that condition's okay. Let's check the next condition. We want to check that the limit, but now we only have to look at the limit as x approaches 0 from the right of our function exists. So we're wondering, does that limit exist? Well, what is that limit? The limit as x approaches 0 from the right of f of x for this function is just the limit as x approaches 0 from the right of root x. And notice we could not approach 0 from the left because we would be looking at values of x that are negative, and we could not take the square root of a negative number and hope to get a real output. Well, remember that all of our limit functions work even if we are looking at a one-sided limit, a limit from the right. So I can still use the root limit law here to pull this limit sign underneath the square root, and I can go ahead and say this is the same as the square root of the limit as x approaches 0 from the right of x. Well, what's this limit equal to? It's the obvious limit, or you can think of x as a very simple polynomial. In either case, we get to do it by direct substitution, so we end up getting the square root of, and I just replace x with the number that it's getting close to, namely 0. Square root of 0 is equal to 0. So yes, the limit as x approaches 0 from the right of our function does exist, and it is equal to 0. That means that our function satisfies the second condition in the careful definition of continuity. Continuity from the right, I should say. Third condition is that this limit from the right has to be equal to the value of the function when we plug our value of 0 that x is approaching into the function. I'm going to put a question mark here. Let's check and be sure that those two things really are equal to each other. Well, we just got through doing the limit as x approaches 0 from the right, and we ended up getting an answer of 0. In part 1, we found the value of the function at 0, and we also got a value of 0. So those two things are equal to each other, and that means that our function satisfies all 3 conditions of the definition of continuity from the right at x equals 0. So we could say, therefore, f of x equal root x is continuous from the right at x equals 0. And what does that mean? That means that, remember in case 1 on the previous page, we already showed that f was continuous on this interval, the open interval from 0 to infinity. Now we've also shown it's continuous from the right at 0. And how do we write that? We can go ahead and say, well, that means that f is continuous on this interval where we put a square bracket next to the 0. And that's because f is continuous from the right at 0. So we can go ahead and say f of x is continuous on this interval from 0 to infinity, and that's exactly the domain of f of x. The domain of the square root of x is the interval with a square bracket 0 to infinity. So we've just shown that f of x equal root x is continuous on its domain, at every x value on its domain. Okay, let's go ahead and think about the following theorem then. A similar kind of argument can be used for any root function, the square root of any algebraic function, or cube roots, fourth roots, and so on. So it turns out, although we won't prove this general theorem, but for each root function you can come up with a similar proof, or you can do a proof that involves the nth root of any function where n is odd and the nth root of any function where n is even separately, to do a general proof that for any algebraic function containing a root, meaning any nth root where n is a positive integer, any of those are continuous everywhere it is, we usually write in here, defined. Or another way of saying it is everywhere on its domain. And what we just showed was that f of x equals square root of x was defined everywhere on its domain. That means exactly the same thing as everywhere it's defined, because remember, square root of x is defined everywhere on the interval from 0 to infinity, the half open interval from 0 to infinity. Well, let's go ahead and use that theorem, even though we didn't prove the general case, but I hope you can see how we would prove it for different root functions from the specific example we looked at. And let's determine where each of the functions that I have written down here is continuous. If I were to look at part A, f of x is equal to the cube root of x. Well, cube root of x, if we want to know where is this function continuous, according to this theorem, I just have to find its domain. In other words, I just figure out for what x values the cube root of x is defined. Now remember that an odd root, such as a cube root or a fifth root or a seventh root, is a little different than an even root, like a square root where the index is 2. For an odd root, you can take the odd root of a negative number. For example, the cube root of negative 8 is defined. It's equal to negative 2, and of course that's because you can take a negative number, and when you raise it to an odd power, such as 3, you end up with a negative answer. So odd roots are different than even roots in terms of their domain. The domain of the cube root of x is all real numbers. I can put in positive numbers, take their cube root. I can put in negative real numbers, take their cube root. I can put 0 in, cube root of 0 is 0. So I don't have that problem that I have with square roots or other even roots such as fourth roots and sixth roots. I can take the cube root, an odd root, of any real number, positive or 0 or negative. So the domain of this function is all real numbers from minus infinity to infinity. And by this theorem, that means that our function, which contains this root, is continuous everywhere that it is defined, everywhere in its domain. So if its domain is from minus infinity to infinity, I can say therefore, and I don't know if you know this little abbreviation that mathematicians use, 3 dots that make a little triangle like this. It's just a shorthand way of saying therefore, and I'm using it here because I don't have much room. Therefore, the cube root of x, stick my little cube in there, is continuous on exactly the same interval as its domain. It's continuous on the interval from minus infinity to infinity. It's continuous at every real number x. Okay, I want you to go ahead and think about part B. It's a little harder than the one that we just did because I don't just have an x in here. I actually have a function of x, 2x minus 10. but it is an algebraic function. Algebraic functions are just functions that are made up of multiplying, dividing, adding, subtracting, and doing powers of x. We're doing the fourth root. Notice it is an even root of 2x minus 10. And I'm going to have you stop the video and try to think about how to apply this theorem to determine where this function is continuous. And after you've given it a try, start the video again and we'll go through it together. Okay, let's go ahead and go through this together. According to our theorem, this function will be continuous everywhere on its domain. So determining where it's continuous is really the same problem as determining its domain. Now remember that to find the domain of an even function, for an even root, sorry, not an even function, but an even root, for an even root, remember that we can only take a fourth root of a positive number or 0. We cannot take the fourth root of a negative number, just like you can't take the square root of a negative number. If you did that, you would end up with something that is not a real number. And in our calculus class, we are only dealing with the calculus of real numbers. So we would get something that is undefined as far as the real number system is concerned. So the domain, remember that whatever we take the fourth root of, in other words, whatever expression is underneath that root symbol, must be something that is positive or 0 at the smallest. And the expression that we're going to end up taking the fourth root of is 2x minus 10. I want that to be positive, in other words, greater than 0, or 0 at the smallest, but I do not want it to be less than 0. I don't want it to be taking the fourth root of a negative number. I'll get an undefined output. So what we want then is that whatever expression is underneath here, 2x minus 10, has to be greater than or equal to 0. Well, can I solve that inequality? Sure, this one is fairly easy to solve because it's a linear inequality. I'll add 10 to both sides, so I get 2x is greater than or equal to 10. Divide by 2 on both sides. I'm dividing by positive, so I don't switch the direction of the inequality symbol. And I would end up with 10 over 2, which would be 5. So x has to be greater than or equal to 5. If you want to write it in interval notation, it would be the interval from 5 to infinity, where again I put a square bracket next to the 5 because of the equal bar that's sitting here. That is the domain of g of x, and by our theorem, that's also the interval on which g of x is continuous. So we could say, therefore, this function g of x, fourth root of 2x minus 10, that function is continuous on the same interval as the interval that represents its domain, the interval from 5 to infinity. And remember what this really means is it's continuous at every number in the open interval from 5 to infinity, and it is continuous from the right side at 5. Okay, so now we've talked about polynomials, we've talked about rational functions, and we've talked about algebraic functions containing a root, and we've said that all of those are continuous everywhere on their domains. What I'd like us to do next is to look at a kind of general theorem that talks about adding and subtracting and multiplying and dividing functions that we already know are continuous at some particular number, and what that means about the sums or differences of those. So let's go ahead and go through this theorem. It says the following: if we know that f and g are continuous at x equal a, so we're already given the information that f is continuous at a and g is continuous at a, then so are the following functions. And it turns out that if we look at the sum function f plus g, that will be continuous at a. The difference function f minus g will be continuous at a. If I do a constant multiple of f, so this is where c is a constant, some real number c, then c times f will be continuous at a. The product f times g will be continuous at A, and also the quotient f over g will be continuous at A. Of course, when we're dividing, there is a little provided that, and you can probably guess what the provided that is. Remember that we're looking at continuity at A. We would not want to end up having a function that involved a division by 0 at A. So provided, and you can probably guess this, g of A is not equal to 0. Okay, and at such a place where g of A is 0, I'll say when g of A equals 0, f over g is discontinuous at A. So f over g will also be continuous at A, except the A values where the denominator ends up being 0, and at those values our function will be discontinuous. And f and g aren't necessarily polynomials or something like that, so f over g is not necessarily a rational function. They can be any functions that we already know are continuous at x equal A. Well, how do we prove such a theorem for these very general functions f and g? Let's go ahead and go through a proof of this statement, that if f and g are continuous at A, so is the sum function f plus g, and all of the others are proved in a similar way. So we won't prove the others, and I'll leave that to you to think about the proofs of 2 through 5. We will just prove number 1. So proof of number 1, and this is sort of a nice proof because it's a very typical scheme for how we prove things in mathematics. When we are given a theorem, we're always given some conditions in the theorem, and then we're given a conclusion in the theorem. And notice what we are given in this case, and we'll also notice very carefully what we are asked to show in this case. We are given certain facts. Notice it says if f and g are continuous at A. That is our given set of facts in this case. We're given that f is continuous at A and g is continuous at A. So let's go ahead and see if we can write out, well, what does that mean for f to be continuous at A? There's a certain definition, a very precise definition of what we have for a function f to be continuous at some x equal A. We have those 3 conditions. I'm actually going to use the shorthand definition, definition of continuity at A, where we combine those 3 conditions into a single condition. Remember, our shorthand definition said f is continuous at A if the limit as x approaches A of f of x is equal to f of A. It really looks like the 3rd condition in our careful definition of continuity, but implied when I write this statement down is that f of A is defined, so what is over here on the right hand side is a number, so it's defined, and the limit as x approaches A of f of x exists, that's our condition 2, and that those 2 things are equal to each other, so that's our condition 3. So this was our shorthand version of the definition of continuity of f at A. If I'm told that g is continuous at A, that's also telling me something. I go back to the definition and I say, well, what does it mean for g to be continuous at A? I'm going to use the shorthand definition again and say, well, that means the limit as x approaches A of g of x must be exactly the same value that I get if I plug A into the function. As x gets close to A, the output values g of x are getting closer and closer to the same number that I get when I plug A into g of x. I'm going to put a little star here by this first condition, and I'll put a little double star here by this second condition. So we're given this information. Star and double star are 2 statements that we are given. What are we asked to show? Well, what are we trying to show in statement 1? We're trying to show that f plus g is also continuous at A. So that's the thing that we are asked to show in this case. If f and g are continuous at A, that's the given. What are we asked to show? We are asked to show the conclusion, which is that f plus g is continuous. So what we are asked to show is the conclusion, and the conclusion written in the theorem is that f plus g, that sum function, is also continuous at A. And that's what I have written here. What we need to show is that f plus g, that sum function, is also continuous at A. Well, what does it mean to say that f plus g is continuous at A? We apply the same shorthand definition of continuity at A, but now we're applying it to this sum function f plus g. And so f plus g is continuous at A as long as the limit as x approaches A of my sum function, which I'm going to write as f of x plus g of x, is exactly the same as what I get when I plug A into my sum function. And when I plug A into my sum function, I would get f of A plus g of A. So this is what we need to show. We need to show that the limit as x approaches A of f of x plus g of x, that sum function, is exactly the same as what we get when we plug A into the sum function, namely f of A plus g of A. So that's what we must show. Well, how do we show that? We usually start with one side of the statement and try step by step to transform it into the other side of the statement. So I'm starting with the left-hand side of this statement and saying, well, what is the limit as x approaches A of f of x plus g of x? Let's see if we can determine that limit using our limit laws. The limit of the sum is the same as the sum of the individual limits. So by the sum limit law, I could break this down and say, well, it's the same as the sum of the individual limits. That would be the limit as x approaches A of f of x plus the limit as x approaches A of g of x. Okay, and that's just using our sum limit law. Let's go ahead then and see if we can determine what each of those limits is. So I'm going to look at this limit separately, and I'm going to add it on to this limit. Well, what is the limit as x approaches A of f of x? I'm going to go back up to my given. This was something that I could assume. So by the star that's up here, let me put that in purple, by this statement, remember by assuming that f was continuous at A, we said we knew something about the limit as x approached A of f of x. It had to be the same thing as f of A. So right here, the limit as x approaches A of f of x, I can replace it with what it's equal to, namely f of A. Okay. I'm going to add on here the limit as x approaches A of g of x. Well, what's that equal to? And by this statement that I put a double star next to, so I'll say by double star, this statement up here, remember we said assuming g was continuous at A meant we knew something about the limit as x approaches A of g of x, namely that it is equal to g of A. So limit as x approaches A of g of x, we could replace that with what we know it's equal to, namely g of A. Great, so what have we shown? We've shown that the limit as x approaches A of our sum function, f of x plus g of x, ends up being equal to f of A plus g of A. And notice that's exactly what we said we wanted to show. That's exactly this statement that I have right here. So if you look from here down to here, we're really saying that f plus g is continuous at A. Because to show that f plus g is continuous at A, we said all we have to do is show that the limit as x approaches A of that sum function is exactly the same as what we get when we plug A into that sum function. And we have just shown that by using the sum limit law and also using the given conditions in our theorem, that f was continuous at A and g was continuous at A. So I can say therefore, remember this is our shorthand notation for therefore, f plus g is continuous at A. We've satisfied, I'll say at x equal A, we've satisfied our shortened definition of continuity at A. The limit as x gets close to A of this sum function is the same value as when I plug A into that function. So f plus g is continuous at A. And that proves statement 1, and the other statements are proved in a very similar way. Okay, so now I'd like us to do a couple of examples that use the theorem that we just talked about on the previous page. We are asked to determine where each function is continuous. Let's look at this first function, 3x squared minus 7 plus x minus 5 over x plus 1. Looks kind of complicated, but let's think of it as the sum of two functions, where I'm going to think of the 3x squared minus 7 as my function f, and I'm adding on this function g, which is x minus 5 over x plus 1. Well, why did I split them up this way? Simply because I noticed this is a particular type of function, and what type of function is 3x squared minus 7? It's a polynomial. If I look at x minus 5 over x plus 1, it's one polynomial divided by another, so g is a rational function. And we already know about the continuity of polynomials and rational functions. If I just looked at f of x, it's a polynomial, and remember that polynomials are continuous everywhere on their domains, but their domains are the whole real number line. So f of x is actually continuous on the whole number line from minus infinity to infinity. In fact, if I drew a little graph of where it is continuous, and here I'm just drawing the x-axis, f of x would be continuous at every value of x from minus infinity to infinity. So it would be continuous at every point along this red line that I've drawn. If I look at the function g, we said it's a rational function. And remember, rational functions are also continuous everywhere that they are defined, in other words, everywhere in their domains. And the only place a rational function is not continuous is at a place where the denominator is equal to 0. Well, where is the denominator of this rational function equal to 0? That would be where x plus 1 is equal to 0, and that would be true if x were equal to negative 1. So g of x is continuous for all real numbers x not equal to negative 1. And at negative 1 it would be discontinuous. So let me go ahead and draw a number line for g. Here's 0, here's negative 1. And g of x then is continuous everywhere except negative 1. So if I draw a green line and each point on the line represents a point where g is continuous, it would be every real number except I need a hole in my line right at negative 1 since g is not continuous there. Well, according to our previous theorem, if f of x is continuous at an x value and g of x is continuous at an x value, so is the sum function, f plus g. So if I'm looking to find out where f of x plus g of x is continuous, it will be continuous on the intersection or overlap of the places where f and g individually are continuous. So f of x plus g of x is continuous on the overlap, or we more formally call it the intersection of the red points where f is continuous and the green points where g is continuous. And that's simply because for f plus g to be continuous at an x value, f has to be continuous at that x value and G has to be continuous at that x value. So the x value needs to show up both on the red set of points and at the same time on the green set of points. And so we are really looking for points that are both here and here. We're looking for the overlap or the intersection of those. Well, the only point that isn't on both the red set of points and the green set of points is this point x equal to -1. So the intersection of the red set of points and the green set of points would actually be equal to the green set of points in this case. Every point x, if I choose any point x, it's on the red set and it's on the green set at the same time, except if I look at x equal -1, that's only on the red set. It's not also on the green set. So f plus g would be continuous at every x value except for -1. So here I'll draw in blue where the sum function is continuous, and it's continuous at all real numbers x except for -1. That's the only point that's not both in the red set of points and the green set of points at the same time. So the answer to our question would be that this sum function is continuous everywhere, I'll say at all real x except for -1, so all real x not equal to -1. You could also write this answer in interval notation by saying it's continuous from -infinity up to -1 and also from -1 up to +infinity. And we could put a union symbol in between those two, meaning that it's continuous in this interval and also, or I should say, for any x in this interval or any x in this interval. Okay, I want you to think about the function in part B and see if you can determine the set of x values for which this rather complicated function is continuous. It's a little harder than the one that we just did, so give it a try. Try to analyze it the way that we did in part A, and then we'll go ahead and do it together. Okay, let's try this together. Again, if you want to, you can think of this as the function f and this fractional expression as the function g. And we can use our theorem about, if we know something about where f is continuous and we know something about where g is continuous, that will tell us something about where f minus g is continuous. Well, why would I separate it into these two functions? I noticed that f is a type of function we've talked about. It's a root function. And g is also a type of function we've talked about. It's one polynomial divided by another polynomial, so it is a rational function. Okay, great. So let's go ahead and think about f of x. It's a root function. And remember we said that a root function is continuous everywhere on its domain. So all we have to do is figure out what the domain of this function is to figure out where it's continuous. It'll be continuous everywhere that it's defined. Remember, for a square root function, what's underneath the square root, namely x plus 3, has to be something that's greater than or equal to 0. We can't take the square root of something that's less than 0. That would be taking the square root of a negative, and it would give us an imaginary output. So f will be continuous when what's under the square root, namely x plus 3, is either greater than or equal to 0, a positive number or 0 itself at the smallest. And we can take the square root of any of those numbers and get a real number output. Well, when is that true? That's true when x is greater than or equal to -3. We just solved that little inequality. Well, over here, let's go ahead and draw a graph of what x values those would be. Here's -3. And again, I'll do that in red. X greater than or equal to -3. I could put a solid dot here, or you can use a square bracket if you want to. It means exactly the same thing. And all points to the right of that are is a graphical demonstration of all the points for which f is continuous. They're all the points that are in the domain of that root function. Okay, let's go ahead and look at g. G of x, we said, is a rational function because it's one polynomial, 10x, or another polynomial, x squared minus 3x minus 4. And we know, just as we talked about in part A when we were talking about a rational function, this rational function is continuous everywhere in its domain. And what's the domain of a rational function? It's all values of x except values that would make the denominator 0. Now in this case, the denominator is a quadratic expression, so I would want to factor that, and I can see that this factors, let's see, into an x and an x. Looks like a minus 4 and a plus 1 would work. That would give me a negative 3x as the middle term. So this would be defined as long as x is not equal to 4, that would make this factor 0, or negative 1, that would make this factor 0. So g is continuous when x is not equal to 4 or negative 1. It's continuous for all real numbers except for 4 or negative 1, where it is discontinuous. Well, let's go ahead and put those down on a number line, and I'll try to draw this number line right underneath the one I did above. And in green, I'll put down a graphical representation of all the places where g is continuous. It's continuous at every real number except for negative 1, which is right here, and 4. So I exclude those 2 points by putting holes in the graph, and g is continuous at all other real numbers x. Well, we are really interested in finding where f minus g is continuous, so I'm just going to put down here, so f of x minus g of x, that difference function. Remember from our theorem on the previous page, the difference function will be continuous at any x for which both f of x and g of x are continuous. So again, just like in part A up here, we're going to want to look at the x values that are in the intersection of the red set of points and the green set of points. Any x value, if I pick this particular one, that's both on the red set of points and on the green set of points at the same time, is going to be an x value where f of x is continuous and where g of x is continuous, and therefore f minus g will be continuous at that particular x value. So we want all the points x that are both in the red set of points and the green set of points at the same time. That means it will be continuous for any x on the intersection, or perhaps I should say in the intersection of the red set of points and the green set of points. So we're really looking for the overlap for points like this purple one that I drew that are in both the red set and the green set at the same time. Notice that I can't choose a point that's to the left of negative 3 because that would be a point that's in the green set but is not in the red set. I also can't choose a point negative 1 or 4 because those would be points that are in the red set, but unfortunately they are not in the green set. The green set has a hole in the graph there. So if we look at points that are in the overlap, that are in both the red and the green at the same time, it looks like, well, negative 3 itself would be in both. Nothing to the left of negative 3 would be in both. We want to exclude negative 1 and 4, so I'm going to put circles there. They are not in the green set, although they are in the red set. And then we would want everything to the right of negative 3 except negative 1 and 4, those two particular points. So this blue graph would be a graph of all points where the original function f minus g is continuous. So that would be a graph of our answer. If I want to go ahead and write it down in words, let's see, I would say that f minus g, our original function, I'm going to write it up here, is continuous at the following intervals, or maybe I should say for or on the following intervals. Let's see, I think it'd be easiest to do it in interval notation. I want to go from -3 up to -1, and I'm including -3 because I have a closed dot here, so I put a square bracket, or anything from -1 up to 4, so I'm going to put union -1 up to +4, or anything to the right of 4. So I'm going to say or, which means union, anything from 4 to +infinity.